In this video, I'll be teaching you guys about absolute and conditional convergence, and it's really just a little bit of memorization, that is all. So let's explain what is absolute convergence. Well, absolute convergence is in the name, right? You take a series, you take the absolute value of that series, let's use yellow actually, take the absolute value of it, and it converges, right? Then you have absolute convergence. Here's the thing about conditional convergence. If you absolutely converge, so if you let's put ABS here for absolute converge, then you also conditionally converge. Conditionally. I'm missing an L. Conditionally converge as well. Okay, so if you absolutely converge, then you must conditionally converge. But if you conditionally converge, right here, then you don't necessarily absolutely converge. Okay, you could absolutely converge, but if you absolutely converge, then you must conditionally converge. But if you conditionally converge, then that doesn't necessarily mean that you absolutely converge. All right. Now, I've been talking a lot about absolute convergence. Let's talk about conditional convergence. So conditional convergence is basically just when you have in most cases you're going to have an alternating series, right? -1 to the power of n times a of n. And if this converges, right? If your alternating series converges, then you conditionally converge. Conditionally converge. Okay? But if you take the absolute value of this, and this series doesn't converge, right? If you take the absolute value of an alternating series, you kind of just wipe out this guy. Then that means you just conditionally converge, okay? So if you wipe out the alternating part of your series and your series no longer converges, then that means you just conditionally converge. You do not absolutely converge. All right? So that's what I said up here as well. And an example of this, to actually help you out, I think I'll leave this here. So an example of this would be the harmonic series. All right? So let's say you have the harmonic series 1 over n. Let's actually use the alternating harmonic series, right? Take a look at this function here. If you use the alternating series test, and if you don't know what the alternating series test, I'll have a video link down in the description for you guys if you haven't covered that yet. But an alternating series test basically has you take the limit as n approaches infinity for the sequence, and if it equals 0, then that's one of the conditions met for the alternating series test. And also, if you take the absolute value of your sequence and it is decreasing, it is monotonically decreasing, all right? So each value, as n gets larger and larger, your absolute value of your function gets smaller and smaller. An example of this would be 1, 1/2, 1/4, right? This is monotonically decreasing, right? Each next value is smaller than the previous one. Then you meet the conditions for the alternating series test. Now there's also another condition where it's like all numbers are positive for the absolute value. That's kind of a given, right? If you take the absolute value of your series, and all the numbers should be positive anyways because you're taking an absolute value. So due to the alternating series test, this guy converges. That's big. Let's put it in red. This guy converges, right? Let's go ahead and take the absolute value of the series. So n is equal to 1. All right? If we take the absolute value, we just get left off with 1 over n, right? It just eliminates the alternating portion of your series. Well, this is just a simple harmonic series, right? Harmonic series diverges. We already know that. But if you want to take the p series test, p is greater than or equal to 1. Sorry, less than or equal to 1, right? There's n to the power of 1, so p is equal to 1. Therefore, the series diverges. So look what we have here. The series converges before we take the absolute value of the series. Therefore, this guy right here, the alternating harmonic series, is conditionally convergent. It is not absolutely convergent. Now, a quick tip to determine whether or not a series absolutely converges or conditionally converges, right? When you do some tests like the alternating series test or your p-series test or limit comparison test, I very highly recommend that you test for absolute convergence first. The reason why is because if you absolutely converge, you don't have to test for conditional convergence, right? You automatically can skip that step, right? But if you test for conditional convergence first, oh, well, now you have to do absolute convergence, right? Now you have to test absolute convergence, and you just wasted some work if you already absolutely converge. All right, so try testing for absolute convergence first when you have a series, and then test for conditional convergence if you determine that this guy absolutely diverges. But if your series also conditionally diverges, well, then that just means your series diverges, all right? For the series, let's go ahead and test absolute convergence first, okay? That's usually what you normally want to do. So let's go ahead and test for absolute convergence. If we take the absolute value of the series, you simply eliminate the alternating portion. So once I take the absolute value of this is plain old simple p-series test. And since p is greater than 1, your series converges. Absolutely, of course. Absolutely, since we did take the absolute value of the series, this guy absolutely converges. Now remember, if you absolutely converge, then you also conditionally converge. So that's why you want to test for absolute convergence first. Now you don't have to test for conditional convergence. You can just say it conditionally converges. So this series, this alternating series, also conditionally converges due to the fact that you absolutely converge as well. So we actually save some work, right? If we tested if this alternating series, using the alternating series test, we determine that this guy conditionally converges, then we would have to take the absolute value and then take the do the p-series test. Okay, well, you just wasted steps there. Okay, you could have just done one single absolute convergence test to determine conditional convergence as well. Let's go ahead and consider the series -1 to the power of n over the natural logarithm of n. Okay, so let's take the absolute value of this to determine whether or not this absolutely converges. The absolute value just removes the alternating portion, so you get 1 over the natural logarithm of n. Well, here's the thing. If we compare this to the harmonic series 1 over n, we realize that the natural logarithm grows actually slower than n, correct? And since we know that the harmonic series diverges, and since the natural logarithm grows slower than n, then natural logarithm also diverges. And we can kind of use like p-series, so to say, to determine whether or not the harmonic series diverges. But we know that since natural logarithm grows slower than n, and we have the series just 1 over the natural logarithm, then that means we absolutely diverge. Okay, let's go ahead and do the alternating series test to determine whether or not this series conditionally converges now, right? Alternating series. So if you absolutely diverge, that doesn't necessarily mean you don't conditionally converge. All right, so we have to test for conditional convergence if we get absolute divergence. So alternating series test, right? Let's say that the absolute value of a of n is equal to b of n, right? Which is just simply equal to 1 over the natural logarithm of n. So does b of n decrease? Well, it does. All right, b of n is monotonically decreasing, right? Because as you increase the value of n, the denominator will grow. That's how the natural logarithm function works. So as n increases, right, you're just going to keep going higher and higher and higher in values. Therefore, if the denominator is increasing, your entire series or sequence is also decreasing. So let's put a check mark next to this. All right, now we just need to take the plain old limit as n approaches infinity for b of n. Well, as n approaches infinity for b of n, we get 1 over the natural logarithm of infinity, which is simply 1 over infinity, which is just equal to 1. So this meets condition of convergence for the alternating series test. Converges. Therefore, you conditionally converge because the alternating series test says that you do converge. But you don't absolutely converge because we took the absolute value of your series, we determine that diverged. Okay, so this series right here only conditionally converges. It does not absolutely converge at all. Let's go ahead and determine whether or not this absolutely conditionally converges. If we take the absolute value of this, we get that we remove the alternating portion, so we just get 3 to the power of n over n squared. Well, here's the thing about this. You could use ratio tests, but we can already determine that this guy converges because we have an exponential in the numerator. When you have an exponential in the numerator, exponentials completely overpower the power function in the denominator. So an exponential over this tiny little n squared, it's going to overpower it. Therefore, this series will be increasing. Right? So if we take the limit comparison test, if we take the divergence test, let's take the limit as n approaches infinity for 3 of n over n squared. We're going to get some indeterminate form for the first thing, right? So we can use L'Hopital's rule. So the limit as n approaches infinity for the natural logarithm of 3 times 3 to the power of n over 2n. And then we take the L'Hopital's again, because we get another indeterminate form if we plug in for infinity here. So the natural logarithm squared of 3n over 2. Okay, well, if you take the infinity of this guy right here, you simply get infinity in the numerator over 2, which is just equal to infinity. And since the divergence test states that if you don't equal 0, your series diverges, this guy does not equal 0. Okay, so this series diverges. Absolutely, of course. Absolutely. All right, so we need to determine whether or not this series conditionally converges now. Okay, so let's go ahead and use the alternating series test. Alternating series test. Well, here's the thing. We don't even need to use the alternating series test. We already know that the exponential here actually grows faster than the power function in the denominator, n squared. So since this exponential is growing faster and faster, your sequence will look something like this, where it's just going to keep getting larger and larger and larger, right? And each tip, each like spike I'm drawing is like the number in the sequence. So it's just going to keep getting larger and larger and larger. That's what your sequence is going to look like. So as if the values get larger and larger and larger, well, again, your series will diverge. So since you have an exponential in the numerator that completely overpowers the n squared in the denominator, you also diverge before taking the absolute value. So you diverge conditionally as well. Now, you wouldn't just call this conditional divergence and absolute divergence. You would just say that the series diverges. So this guy diverges.